Things are okay.
Also, can anyone hear me on the speaker?
Chris, it is on. Yeah. And then Chima, and then one more.
Good. Good.
Yeah, we have such an early schedule. Right? There'll be more. Right. Well, I mean, here, this is mostly really a celebration. We'll see how the crowds do.
Okay.
I see. I wonder how many people will come to Okay.
Okay, so everybody, please take a seat. We're a couple minutes over, and both Chima and I are a little bit anal about timing. I'm just kidding. No, I mean, just for the sake of keeping things on time, especially because the private portion of the defense is right after this. So we would like for Chima to get a little break. So, so thank you, everybody, for coming at these insane hours of the morning. I think this is probably the earliest PhD defense that I've ever been to. And I'm a morning person. So thank you everybody for coming to Chima's public portion of his PhD defense. I would like to thank Chima's family and friends for coming, the local people for getting up this early, and the committee members for being here on time. Jennifer G, Peter Gao, Dave Shabinov, and Dimitar Sasolov, thank you for coming in. Like most of us know Chima now. I have to give like a 2-minute introduction because I have to. But I think that we all know how cool Chima is. He arrived here in 2017. He arrived here in 2017. To join our PhD program. But what most people might not know is that he was here before, as an REU, like as a summer REU. And he worked with Willie Torres for the summer in 2016, I believe. So somehow we managed not to scare him away, and he came back. And like those of you who have been following Chima's work here, you guys probably know that he has done a lot, not only in terms of science, but also in terms of outreach and DEI. So I'm going to highlight, and I have to look them up because they have complicated names. I'm going to highlight just 3 of the DEI efforts that he has led. He was part of the first cohort of the National Astronomy Consortium Outreach Fellows, which is a program designed to improve the diversity in STEM. He was also a very active member of the IDEA group here at the CFA. And he was a one-on-one tutor for the ONAKEDA program, which actually tutors middle school kids and high school kids from underrepresented groups. He also has a really nice article in New Scientist magazine that has caught a lot of attention, and the title is The Hunt for Extraterrestrial Life. That's just in terms of outreach. Scientifically, he also has been great. Like somehow he has managed to be in the Harvard student list since he got here. I don't know how. And I do know how, but I don't know. And also, like, he, I see him as this, like, this is the other thing. So most of you might not know that he started to apply to become an astronaut, a NASA astronaut, since he got here. And I think that in the back of his mind, he's like, if I ever go to another planet, I really need to know that the weather is better than in Boston. So he decided to do his PhD on trying to figure out weather in exoplanetary atmospheres. So he undertook this project at the beginning of his PhD, and he has, it was a lot of work, but I think it has paid off. And as Chima will show you next, it was pretty good. I must say, to finalize, because you don't want to hear me, you want to hear him, that so far he's a co-author in 13 publications, 4 of them as first author, and those are the bulk of the dissertation that he's going to present and defend today. So with that said, take it away, Chima.
Thank you. Thank you very much. Yeah, thank you very much for that wonderful introduction, Mercedes. And as she said, I'm going to be talking about my work, my thesis work on exoplanet atmospheres. And just a quick overview, what an exoplanet is. It's just a planet that orbits a star different than our own. And we've found a multitude of exoplanets. We've found over 5,000 exoplanets orbiting over 4,000 different stars. And just to show that we found exoplanets all around us, I have a mosaic video of all the different planets that we've discovered over time. And each ding here represents a new planet being discovered, and the circle corresponds to that. So as you can see, we've discovered a wide array of exoplanets everywhere around us. But not only have we discovered many exoplanets, we've found many different types of exoplanets. And here is the planets in our solar system, the ones we all know and love. On the y-axis is the size of the planet. On the x-axis is the distance the planet is from the star. And now over plotting all the planets that we've discovered, you can see that we found very different types of planets. Very different from the planets in our solar system. And in fact, we found planets of classes that we've never expected to find. For example, hot Jupiters. Where hot Jupiters are planets that are larger than, around the size of Jupiter, delineated by this line, and much closer to their host star, delineated by this line. And as you can imagine, when we initially discovered these types of planets, we were very perplexed by them. Yet these are the types of planets that I'm going to be, that I did my thesis work on because they're much easier to observe. Just to outline how close these planets really are, here's the orbit of the planets within our solar system in blue. And you can see the furthest out hot Jupiters are much closer than the orbit of Mercury. So these orbits are basically kissing their host star. And as you can imagine, because of this, they have exotic conditions on those planets. The temperatures on the atmospheres are 1,000 to 3,000 Kelvin, which corresponds to up to 5,000 Fahrenheit, which is the temperature in the exhaust of a rocket engine. They have exotic winds, supersonic winds, excuse me, meaning that the winds are going faster than the speed of sound in that atmosphere. They're tidally locked, meaning that the same side of the planet faces the star. And they have exotic metals in the readily available in the upper atmosphere of the planet. So they're literally raining down liquid metals. Could you please turn off the camera? That's distracting. The light. Okay, and we found out about this by probing. We didn't find out about this just by discovering them, but we had to probe deeper into their atmospheres. And so when you look at the atmospheres of planets within our solar system, we see a wide diversity of atmospheric characteristics, where none of the atmospheres are alike from one another. However, one commonality between all of these atmospheres is that they have some form of clouds or hazes, which I will use the term aerosols, which is a cloud, a haze, or both. But now moving to exoplanets, so far we've observed the atmospheres of around 150 exoplanets, which is not many relative to how many we've discovered, but even still we find a wide diversity amongst those exoplanets. The one thing again though that we find within all of these atmospheres is that there's some level of aerosols in them. But why? Why is there some higher level of aerosols in some and not in others? Okay, so to put it into context, if you have a weatherman who has no idea what they're doing, they might say, oh, it's gonna be a beautiful day. You prepare for this, gonna be going out, shorts, t-shirt, and then this is what you look like. You get dumped on. It sucks. And this is how a lot of astronomers feel, because when they observe atmospheres that have high levels of aerosols, it prevents our ability from probing them. And so what my thesis objective was to predict was to find a way to predict which atmospheres have higher levels of aerosols than others. And to go about explaining to you the work that I did through my thesis, I'll first talk about how we observe atmospheres. Then I'll talk about the specific method that I use to try to predict which atmospheres have more aerosols. The specific way I observed to make sure this project was successful, the analysis I did once I obtained the data, the results I found, future work, and most importantly, acknowledging everyone who helped me. Okay, so first, exoplanet atmospheres. Observing exoplanet atmospheres allows you to find the conditions and internal structure within the planets individually, but even done statistically, you can understand the migration, formation, and evolution of planets as a whole. And the specific way that I use to study exoplanets is transit. When the planet passes in front of the host star relative to our line of sight, the light coming from the host star diminishes due to the planet's presence. And this you can see in this light curve of our observation shown in yellow. Is my mouse there? Yes. Shown in yellow. And that's how we find the planet, observe the planet. That's easily said, but in reality, this change in depth is very small. So for an Earth-sized planet orbiting a sun-like star, this is about 90 parts per million, which means that of a millionth of the signal, only a millionth of the signal is being changed by the planet. And to make matters even more complicated, to observe their atmospheres, we do this in multiple wavelengths of light. And the reason why we do this is because depending on the molecules in the atmosphere, it attenuates more light at a given wavelength. And this cartoon does a great example of showing this, where the specific molecule at 5.9 microns, shown in yellow, absorbs much more light than at 6.6 microns, shown in green. And so what we do to probe the atmospheres is we take all these light curves at different wavelengths and compare the depth, so how deep this line is, relative to wavelength, which is shown here. So the purple plot corresponds to the purple light curve. The yellow plot, which is the largest depth, corresponds to the yellow point here. And the green light curve here corresponds to this green point here. And so that's how you observe a transmission spectrum. But just to give you a little more understanding of how it works, we're going to talk about everyone's favorite math, geometry, as this smiling kids show. Everybody loves it. Okay, so when you do transmission spectroscopy, most of the light is going to be blocked by the planet itself. And you're only seeing the light that's passing through the upper limb of the atmosphere. The reason being is because deeper into the atmosphere, the light may not pass all the way through because it's being attenuated by too much of the atmosphere. To make matters a little more complicated, when you include aerosols, so clouds and hazes, that can block even the light going through the upper atmosphere. So the question is, which atmospheres are affected by aerosols? Unfortunately, pretty much all of them. Studies have shown that 93% of atmospheres have some level of aerosols in their signatures. And on average, it mutes the signals by 1/3. So in the blue here, this is the water feature. And the light blue shows what the signal would be without aerosols. And the purple shows what the signal is when you incorporate aerosols. And another feature that we look at is the sodium and potassium lines. Sodium and potassium. And the effects of clouds are shown here. Where the blue, you see strong absorption feature with wide bands and a high peak. But then as you go up from orange to all the way to red, you see the effects of clouds diminish this. And it's the same case with hazes, but you also get with hazes a slope going from blue to red. So a downward slope going from blue to red, as well as a muting feature. And because aerosols mute the signal, for my research, I use the strength of the sodium signal as a proxy for aerosol levels. And bringing this together, I know this might be a lot for a plot, but this is often used when trying to understand, when talking about aerosol formation rates. And just to break it down, as we've shown here up on the top, the green, the sodium signals to the left and the water signals to the right. And you can see on the top, it's very strong signals. But then as you move lower down, the signals become weaker. And even here, you almost see nothing. And here, it's extraordinarily muted and a slope indicative of hazes. But why? Why are we seeing these differences in atmospheric conditions between planets? Being able to predict which atmospheres have aerosols would be useful for optimal observation time, as well as telling you important physics. Because of that, much work has been done to try to understand why what could be correlated to aerosol formation. However, a lot of those observations have had contradictory results, as well as being dependent on multiple parameters. And so that brings me to my specific method that I use. And this method uses a very simple idea from lab experiments. And in a lab experiment, what you would do when you want to find what causes a specific observable, you would repeat an experiment multiple times while only changing one or two parameters at a time. So you can isolate that specific parameter that causes that observable you're considering. And that's exactly what we're trying to do here, except because we can't change the heavens, we have to find planets that are very similar to one another inherently. And that's what we did. I found 7 planets shown here on the left. There's their call signs that all share similar parameters to one another. And so the objective is to find planets that, to find a correlation with the amount of aerosols and some other parameters, something such as the planet, something related to the planet, to the host star that the planet orbits, or some sort of dynamics between the planet and the star. And we want to find a simple correlation with the level of aerosols, which I said I use the sodium signal as a proxy for that, and some other parameter. However, it's important to make sure that your sample is not contaminated. So what we don't want is this, where you think you have planets that are very similar to one another, but in reality, some of them are significantly different on the parameters that we're interested in. And to avoid that, I reanalyzed data from three different space telescopes, 6 different ground-based telescopes, combined all of that data and reanalyze it in a homogeneous manner. And the advantage of this is that it reduced biases from different analysis methods, as well as increased the precision of the parameters. And what we find is that these planets are truly very similar to one another. And on the red and blue are the planets that I observed, are the planets that I'm interested in my sample. And the light green and gray are parameters of other planets. As you can see here with the y-axis mass, it's very flat. And the equilibrium temperature, planetary gravity, radius, planetary density, and the amount of energy that the planets receive from their host star are all very tightly constrained to one another. However, there are still a few parameters that are different from one another, and those being metallicity, which is the abundance of elements heavier than helium in the host star, and possibly high energy radiation. And I say possibly because we use proxies to measure high energy radiation, this being radiation such as X-rays and extreme UV radiation. And to explain why these parameters could be correlated to cloud formation, or to aerosol formation, first let me talk about metallicity. So metallicity, if you have elements heavier than helium in your atmosphere, that means that the material that makes up the clouds will then be heavier. And then that will cause the clouds to sink down deeper into the atmosphere, being unable to affect our transmission spectra observations. And just as a reminder, clouds mute the signals that we see as a blanket, at least in the wavelengths that we're interested in here. Now what about high energy radiation? So hazes form similar, we expect hazes to form similarly as smog does in Earth. And that is light comes in and dissociates molecules in the atmosphere. And then those molecules recombine to form the hazes. And so it's easy to imagine if you have more amounts of light able to dissociate those molecules, then you'll form more hazes. Just as a reminder, hazes again blanket the signals, but then have a signature from a downward slope from blue to red. Okay, so we found that most of the parameters are very similar to one another, aside from a couple. But how do the transmission spectra look? They look quite different, actually. You can see here in the blue, WASP 96 is one of the clearest atmospheres that we've observed, with strong sodium signal here. Contrarily, WASP 10 is completely flat, or relatively flat, indicative of high levels of aerosols. And WASP 6, in red, is somewhere in between, with muted levels of potassium and sodium signals, and suggestion of a slope here from blue to red. Okay, so this is justification that finding that 3 of these planets are different from one another is justification to observe the others and see if we can find a trend. And so we have to observe them. And this is actually a picture that I took after finishing an observing run. You can see here by the slanted 6:45 a.m. how jaded I was after that. Okay, so these observations and analysis was done in collaboration with Access. I really appreciate the help that they provided in the entire process. And what we do for these observations is we use one of the Magellan telescopes, where it's BADA, it's this one right here. And so let me go through the process of making a successful project. First, you come up with the idea. We did that. Then you have to propose. My proposal writing is much better than Oliver Twist, I'd like to point out. Right. And then once we write proposals, we have to make the observations and then analyze the data. I will talk about the data collection process and the analysis in subsequent slides. But for full circle, the final step is after you make the analysis, you have to first consider if the data quality was good given the conditions of the night, and then how many other observations of that same target you need. Because we combine observations from multiple different nights to improve the signal of the data. But this isn't a one-off. You have to do this repeatedly. I did this every season, reproposed, reobserved, analyzed the data, and then reassessed how much more I needed. So let me talk a little bit more about the observations. Before we even get to the telescope, we have to design a mask. And this mask blocks out all light except for the light from the stars that we're interested in. As you can see, it's pretty much a metal sheet with tiny little holes on it. And the reason that we need multiple holes, because we're only observing one star, or we're only interested in one star, is for two reasons. One, we need to make sure we're continuously tracking the sky throughout the night properly. And two, we have multiple stars similar to the star that we're looking at to correct for systematics. Okay, designed our mask, go to the telescope. That's me at the telescope. I'm very happy because this is before the 8 hours of observing in the middle of the night. But still awesome, very fun. It actually doesn't show the instrument that I use. It's on the other side. But that's what it is. It's IMAX, multi-image spectrograph. And yeah, so I actually started doing these observations from the beginning of my PhD work, my first year. I remember my first time observing, like through conversation, I was talking to some people and they were like, the cost to make these observations work per night is around $5,000 to $10,000. And I was like, holy crap, if I mess this up, this is a year's worth of rent. So I learned how to observe well pretty quickly. Okay, we take these observations, and then what do we do with the observations? We have to analyze them. And the analysis process is not easy. This is what we want. Looks amazing, great light curve. You can see that the data tracks the model, our expected model, very well, and with only a small amount of random scatter around the model. That's what we want. That's what we should have. That's what we really get, though. Not awesome. Not awesome. There's a lot of systematics going on here. And to make matters even worse, the systematics are unique for every single night. So you just have a whole bunch of mess going on here. And the challenge is to correct these systematics for every night and every wavelength as well. And that's actually 70% of the work that I did for my PhD. But I'm going to brush it over in 2 slides. Okay, slide 1. We used machine learning algorithms. We used two separate machine learning algorithms to model the systematics and detrend the data. The first shown on the right is principal component analysis and Gaussian processes. And the second shown, first shown on the left. Second shown on the right is common mode correction combined with polynomial regression. So those are the 2 analysis methods that we did. But the question is, which one's better? There's only one way to find that out. Fight! So that's exactly what we did. We pinned these two machine learning algorithms together by testing them with synthetic data. But whether this is Rocky 1 or Rocky 2 depends on the specific type of data. Common mode correction and post-polynomial regression was more effective with data that didn't have a lot of systematics per wavelength. Whereas principal component analysis and Gaussian processes was better with data that was more complex with a wide scatter and noise per wavelength, or systematics per wavelength. Okay? So I use both methods separately depending on the data set. And once I use these methods to detrend the data, that was slide 2, we're out of it. We take those light curves to produce the transmission spectra such as these. Okay, but now we need to interpret the transmission spectra that we observed. How we do that is also very complicated. I'm not going to go through in detail how this works. Just look at that and know it's difficult. But in essence, what it does is it takes in the data, it compares it against models continuously, and eventually it spits out the probability that a specific parameter or specific features in the atmosphere correspond to presence of molecules in the atmosphere of the planet. All right? So first step is, after we collect the data, is we detrend it from ugly to beautiful. We produce the transmission spectra, and then we run it through retrievals to give us what physical parameters we're actually seeing, or what physical features we're actually seeing. And then let me show you my results. What did I get from doing all of this? First, let me show you WST96b. WST96b was originally analyzed with a different telescope through a different group. And what I did is I reanalyzed that data, and then we also had 2 observations with our own data, and I analyzed that. And what I found is that both separately show strong sodium signals indicative of very little aerosols, and then I combined the data to improve the precision. Where here black is the combined data from a given telescope, and here on the bottom is the combined data from both telescopes. Next, I analyzed WST25b and WST124b. And I found that both of them don't have strong signals. For WST124b, I do want to caution, though, that the precision of the data was not as high as other data. And even though we don't see a signal, it's not necessarily that there's not features in the atmosphere, but just our data precision cannot capture them. But regardless, let's see what I get. I put in all of the observations. There were 2 previously observed and the 3 here. And do I find a trend? Yes. Yes, I do. Very nice, very nice. This trend shows that aerosol levels are correlated to metallicity. As I said, this could be explained because the higher abundance of heavier metals brings the clouds lower into the atmosphere. And so we not only find a tentative trend for aerosol formation, but we also show that this technique can be used and is effective. All right, so just in summary, what have I found? Aerosols are ubiquitous in exoplanet atmospheres. But what specifically controls the formation of aerosols is not well understood. I identified a technique to find correlations between aerosol formation rates and specific observable parameters. I found this technique. With this technique, I found 7 planets, which I homogeneously reanalyzed to try to isolate if there was a trend, which I did find a tentative trend between metallicity and aerosol formation rates. And I want to stress again that this is a prime method of isolating specific system parameters to find correlations in atmospheric characteristics. Okay, so how could this work be used in the future? To give a little bit of context, let's see how exoplanet observations have progressed over time. First was the observations of the first exoplanet atmosphere in 2002, 2002, 20 years ago. Beautiful observation, great stuff, but HST was not initially designed for observing exoplanet atmospheres. So it's like you lost your glasses and you use your friends. It works, but it's definitely not ideal. And then in 2007, ground-based telescopes did the same, but also these telescopes weren't initially designed for observing atmospheres. And 2017 is an important day for at least one person in this room, and that was, I became a grad student. Observed my first transmission spectra, great times. 2022 was incredibly novel, 20 years later. And that was James Webb observed transmission spectra. And this telescope was actually designed with initial intent to observe exoplanet atmospheres. And just to show how much it progressed, previously on white, shown here, was the state of the art before James Webb. And in these colors, red, blue, and yellow, is what James Webb did with one observation. You can see that the wavelength coverage is wider, the precision is better, and the resolution is also better. And then looking on into future, other things that we're excited for is the ARIEL telescope in 2029, hopefully 2029, which is intended to observe 1,000 exoplanet atmospheres. This will literally increase the number of atmospheres we've observed by order of magnitude. 2030s, 2040s, the next generation of ground-based telescopes will come online. And these telescopes will have the high enough resolution to resolve specific signatures such as oxygen. And deep in the future, the Habitable Worlds Observatory hopefully will be launched. And this, as the name indicates, is intended to look at the atmospheres of planets, terrestrial-sized planets. And so there's a lot of great things coming with many planets, many more atmospheres being observed, with much more precision. But it's important to optimally use that data. And methods such as these, using similar planets to isolate specific observables that you're interested in, can be used to produce optimal production from these telescopes. So exoplanet atmospheres in general might not be clear, but the future of their study is bright. Okay, so this concludes the science part of my talk. And now I want to begin on my acknowledgments. I think the acknowledgments are very important because you need to show that your success is not done in isolation. I also think it's very difficult to do acknowledgments because it's hard to give everyone that helped you along the way proper recognition. But I will try to do honor to to do justice to my heroes, my allies, and those who I look up to. But no, this is not encompassing. First, I'd like to acknowledge John Levine. He was my first physics teacher in undergrad. I was not very good at physics originally. In fact, my first test, I got the third lowest grade. Very devastating. I actually was thinking about leaving science altogether. And Dad can attest to this. But John, he wouldn't have that. He wouldn't have that. He would stay with me after every class, multiple hours, to try to make sure that I understood the material. And it was very useful, very helpful. And in fact, the next test, I got the second highest grade. And I know his life was ended too soon, but he definitely touched me in that life. In undergrad, I also had a couple internships. And both of them were very amazing. They both strengthened my skills, and I really like to acknowledge those who made those internships happen, my advisors, and then just the cohort that I had an amazing time with. Thank you, my committee. Thank you for giving me recommendations throughout my PhD. Thank you, Peter, for coming here. Really appreciate y'all. Mercedes. Mercedes is awesome. Yeah. Amazing. And I have a lot of stories to tell you about how Mercedes helped my career in so many ways. But I'm just going to limit myself to one. When we started graduate school, when everyone starts graduate school, we're not the most productive scientists. We have some deficits in our skill. And one of my deficits was my coding ability, which was Mercedes was unfazed by. She would actually spend multiple hours with me, sometimes even multiple days a week, going line by line to debug my code. It was code that we would work on through pipelines, and also code that I made myself, which is already impressive for a senior advisor. I've never had that be done. But what's even more impressive is this woman didn't even know Python. She was able to read the code, some of it which I wrote myself, figure out what's going on, and then teach it to me from a language she did not initially know. That's amazing. And just overall, Mercedes, I haven't had an advisor that I respected and looked up to as much as you. And one that I feel like respects me equally so. Thank you. Mercedes' group is fun, knowledgeable, and just like overall a collectively good people to hang out with. I've had productive discussions with them, and I've had many fun discussions with them. I just also want to mention, if you thought this talk was like clear and easy digestible, definitely Victoria's help. If it wasn't, I totally botched the job, so don't come to her. The unsung heroes, the administrators. I think also to represent how unsung they are, I had to dig so deep for these photos. I didn't get all the photos, but like, y'all are like low key to the max. But very, very helpful. Thank you. I got a great family. Y'all are amazing. Y'all are inspiring. Y'all are supportive. Ridiculously successful. Like, we have a family reunion, there's so many doctors, people must think we're running a clinic. I think a lot of people have to look outside their family for inspiration, but I'm very fortunate that I don't. Thanks for being a great family. Also, Heike and Michelle, you guys literally flew across the Atlantic to be here for this moment. If that's not a loving and supporting family, I don't know what is. Thank you. Mom and Dad, you guys raised me to be the man I am. And I think, in fact, y'all's support actually complemented each other very well. Mom, your confidence is infectious. And I know I'm the confident man I am today because of you. And Dad, your joy for science and learning is definitely what inspired me to become a scientist. Thank you both for doing a wonderful job raising me. I have a lot of friends. But I got a lot of good friends. And that's what's really important. Grad school was definitely hard for me for many reasons. But having y'all with me, supporting me, really made me come out of here not cynical as hell. You guys got my back, whether we're gonna completely nerd out to the max, 16 people deep in a basement apartment to have a LAN party. So many adventures. Most of them are shredding, but also, no matter what it is, it's amazing because you guys make the memories there. Lastly, but not least, Marie. Marie, you're an amazing girlfriend. I love you a lot. We've had some great times. And I definitely know it's really hard because we have to say goodbye a lot. And that's never easy. And it doesn't get easier. But I wouldn't trade it for the world because you are my world. Thank you so much, Team mcbould.
Thank you, Chima. As you say, good stuff. And if anybody's not gathered, and at this point, and you guys have a quick Scottish word, if everybody's not too emotional, that's kind of. I have a question right now for Chima. Please speak up. Or raise your hand.
Can we ask questions?
Of course.
Okay, so you talked about the future of your research. So is it possible that your research could possibly lend itself to people inhabiting other planets? When you look at the mixture of the atmosphere and determine if it's hospitable to human life?
Yeah.
Is that the path forward, or is that what you all are hoping to do with your research?
I mean, I think low-key every exoplaneteer is aiming to do that. We do it at different angles, and I do believe that the work that I was doing, it was specifically for hot Jupiters, but as I was saying in the end, it can be transmitted. Hot Jupiters are planets that are large, close to the host star, but it can be transmitted to terrestrial-sized planets, which is the ones that we're looking to probe the atmospheres for in consideration of life. So yes, the answer is yes. I believe this is a stepping stone to more in-depth understanding of terrestrial-sized planets.
Thank you.
Oh, no. Okay, so go ahead and then there's one.
Chima, based on everything that I've seen, I'm a friend of your mother's since high school. You have made us proud. I would like to know what your future plans are.
Oh man, what a question.
In the next 10, 15 years.
Okay.
In terms of your profession.
Okay. Is this an interview? Okay, so in the near future, I'm actually not staying in academia. I will be here for 3 months to continue the research that I'm doing now. But after that, I don't see myself staying in academia, at least for the foreseeable future. So I could say maybe 10 years I'll be back, but most likely not 5. Yeah. That's what my plan is, to leave academia.
Make money.
We'll see. I got time to figure it
So
out.
actually, Chima, I got some news for you, but I'll tell you later.
Chima, great talk. I was wondering, why do you expect there to be correlation between aerosols and like host star metallicity?
Right, so the metallicity of the host star represents the metallicity of the protoplanetary disk in that planet formed in. And assuming that because the star had higher metallicity, then the planet would also have higher metallicity because it formed in the protoplanetary disk that the star also did. And then that brings to you the situation where I said that you have higher weight of seed particles that form the clouds, so then those seed particles will form deeper into the atmosphere.
Hey, Chima, awesome talk. You talked a lot about hazes and clouds blocking the light in the atmosphere, but how do you tell the difference between if there is clouds or if there's just, these elements are just not present, or there's just no atmosphere?
God, that's a great question. So I'm working with hot Jupiters, so there's an atmosphere. But the abundance of specific molecules does dictate how strong the line is as well. So we do assume that because these are hot Jupiters, they do have their own inherent abundances of these substances. So it is going to be degenerate with the overall abundance, but that is why we look in the optical, because the scattering slope in the bluest range dictates oops. So there's a degeneracy between abundance and cloud levels, and if you have the scattering slope, it allows you to constrain the abundance levels. And the scattering slope is seen in the optical around 4-ish microns. And if you see that scattering slope, then you're able to, with the retrievals, constrain the amount of molecule in that atmosphere, of the specific molecule in that atmosphere. So so you need a combination of both. So for example, in the water feature, you'd be completely degenerate, but if you look in the potassium feature, which also has the blueward wavelength, you can break that degeneracy.
Chima, so you mentioned that there was another parameter that you were interested in terms of potentially having an impact there, which was the UV and X-ray environment of these planets. So have you looked into that? Is that part of future work? How does that play?
Great question. Yes. So I did preliminarily look into that, which I showed there with the calcium RHK signal and the near UV flux, which is, the calcium HK is not a terrible proxy, but to get the best understanding, you would definitely need to do actual observations. And so the hope is to observe with XM Newton and HST COS. We've applied twice to do that. We're unsuccessful, but I literally was talking to Mercedes like 2 weeks ago. We might as well apply a third time.
Even though this one is staying in academia, he's going to put an logistic proposal.
Hey, Chima, great talk. So you were showing really well how hard it is to do these observations, right? These are hot Jupiters. What about terrestrial planets? Are the methods very different to observe atmospheres from them?
So the technique that we use, transmission spectroscopy, it's the same technique, but it is insanely much more difficult. So right now we have attempted transmission spectroscopy with terrestrial planets. We haven't found strong signals with them, but then that could also be the question that Lika said is, if they have no atmosphere, you also wouldn't have a signal. So the terrestrial planets that we've been looking at are really close to their host star. And they're also, the host star is much more active in general. So they could be stripping the atmosphere. So all in sum, still very difficult. Haven't had any success with terrestrial planets.
Okay, if I can keep track. So Jonathan had his hand up, and then there was a couple questions back there. You want to go ahead, Jonathan?
Yeah. So Chima, great talk by the way. You mentioned the 3 ways in which JW is better than Hubble in terms of wavelength range, precision, and spectral resolution. And I'm wondering if you could have only one of those much better in a future spacecraft, which one would make your analysis easier?
What is this, like Sophie's Choice? This is a tough one. Okay. All right, so the options: wavelength range, precision.
Like, what's limiting you the most when you're trying to get these?
So when you're trying to understand clouds, having a wider wavelength range would help a lot because, as I mentioned in the slide, clouds blanket the signal in the optical. But it is possible that they have signatures in the infrared. So that would be very useful. When you're looking for specific molecules, as I said, spectral resolution improves immensely. So for example, we couldn't have found isotopes in atmospheres using the resolution of HST, but we did with James Webb. Precision, wavelength.
So you want it all, basically.
Yeah, I want it all. I want it all.
All right, cool. Question back there?
Yeah, so you did a lot of work in your initial phases of your analysis to combine observations from multiple ground-based observatories and from space-based observatories. So I'm just wondering, like, what that process looked like and how much work it took, because I know every, like, different type of observation is done in its own unique way, and you, like, chopped all that data together to do a comparison.
Yeah, it took a lot of work.
Yeah.
So each analysis is unique. And 2, you have to consider how to combine it properly.
Yeah.
So like, let me just give you one tidbit of an example of where it was very difficult. One of the space telescopes that I used was TESS, great telescope, but it doesn't have that high of a resolution. So there was a contamination between another host star and the star, or another star and the star that I was interested in. So I had to actually decouple the signal that was merged from both of them into individuals. So that is one example of how that's a specific consideration for that telescope, which I wouldn't have had to consider for some of the ground-based telescopes that had higher resolution. So, a lot of work, difficult.
Okay, is there any more questions? Right, go ahead.
So you said the metallic clouds hung heavier, or hung lower. You looked at their height to determine, to make your observations. So my question is their height dependent on the mass of the planet, the density of the planet, and if so, how do you know that, and how do you factor that into the calculations?
So the mass is dependent on the density, or the cloud levels likely would be dependent on the density. Fortunately, because we're doing a control sample, the planets all have extraordinarily similar densities to one another. So actually, in the plot that I showed in the end, right here, this is unnormalized by scale height, which is correlated to density. And you still see this trend when you do that. But even if I didn't normalize it relative to scale height, the trends pretty much holds because they are so similar in density.
And how do you know the densities?
So I know the densities because I reanalyze all of the ground-based and space-based observations of the system. So planetary density is right here. So I used 6 of the telescopes from the ground, 3 telescopes from space to homogeneously reanalyze that.
Okay, any more questions? If not, oh, okay, go ahead, sir.
Okay, as someone that is not very knowledgeable about this subject, I was wondering that, so if I'm understanding this correctly, the aerosols are metallic in property. Is that correct?
So in hot Jupiters, we expect all of them to have some sort of metals in them.
Okay. And does that affect the study for, say, non-metallic aerosols? Or like if you were to migrate this data to other planets as we were discussing earlier?
Yeah, so that you would not expect the same trend that you see in these types of planets in terrestrial planets. And I'm not advocating for transposing the specific trend. I'm advocating transposing the idea, which is isolating specific terrestrial planets that are similar to one another, except for one or two parameters in which you can then find correlations with.
Okay, any more questions? If not, thank you, Chima, and in 10 minutes we are moving to the private portion of the defense, but for people who want to stick around, we should be done by noon, right, committee? So yeah, at noon we will come out, or earlier. So thank you.
Ooh.
Fun time.